Hello everyone, I'm Nakamura from the Graduate School of Okayama University. Now I'm going to talk about secondary side resonating LLC converter for reducing transformer voltage in high-power applications. Let me start from the background. Power suppliers in server racks have converted 400 DC voltage to 12 DC voltage and then to lower voltage to drive CPU or memories or other equipment using POL. However, the long 12 voltage wiring causes a lot of conduction losses. In addition, with the development of AI or 5G, servers now consume more and more power. Also, to improve efficiency, CPU and other equipment are handling lower voltage. Considering this background, the structure of server racks is expected to be such that power suppliers is distributed at high 400 DC voltage close to the motherboard and step down significantly by isolated DC-DC converter placed on the motherboard. At this time, such DC-DC converter must be too small and quick response and able to achieve high step-down ratios. Nowadays, phase-shift bridge converter are used as such DC-DC converters. This converter achieve quick response and the use of center tap rectifier with huge diodes makes it easy to achieve high step-down relations that allows a large current to flow. However, due to the leakage inductance of such transformer, this converter cannot be driven at high frequency. Therefore, passive element cannot be too smaller. So we focused on our attention on LLC resonant converter. First, the converter has a resonance capacitor to cancel the reactance of the leakage inductance of transformer. In addition, soft switching can be achieved by designing a transformer phase difference. Therefore, it is easy to drive at high frequency and to make passive element small. Secondly, the converter has two resonance points, blue resonance point which determines the output impedance and red resonance point makes boost mode. Even if the output impedance is designed to be very small at the nominal frequency, the output voltage can be varied by changing the switching frequency to respond quickly to load change. Finally, high step-down ratios is easily achieved by using center tap rectifier with few diodes on the secondary side. However, this converter has a problem. The LLC resonant converter requires quick response and should be designed for high Q factor. However, designing for high Q factor leads to large resonance voltage in resonator. Then the size of the transformer or capacitor shield must be bigger for isolation. We want to break these relationships. Now, I will talk about the objectives of the approach of my study. The objective of my study is propose a new LLC resonant converter with suppressed high resonance voltage. The new LLC resonant converter is very small and achieve high step down ratios and quick response. Approach is to move the resonator to the secondary side. If the resonator is moved to the secondary side, that resonance voltage is divided by turn ratios. Therefore, I developed a new LLC resonant converter with the resonator moved to the secondary side. However, moving the resonator to the secondary side is not easy. Because LC resonator and center tap rectifier cannot coexist. There is always DC current on the secondary side of the circuit. Therefore, resonant capacitor cannot be placed on the secondary side. It is necessary to consider an alternative rectifier to the center tap rectifier in order to achieve high step down ratios to place a resonator on the secondary side. I focused on my attention on current double rectifier. If you use current double rectifier, you can place the resonator outside the DC current path. However, it is not small enough as it requires 2 inductor cores. I propose the use of coupled transformer. This coupled transformer behaves just like a transformer and is small because it has only iron cores. Only one iron core, sorry. However, this idea is not enough. Conventional LLC resonant converter have 2 resonance points, this blue and this red. Therefore, the boost mode operation could be realized even if the output impedance was designed to be small at the nominal frequency. In this circuit, there is only one resonance point, this blue point. The nominal frequency cannot be designed at the point of lowest output impedance. So I thought that the resonance points could be increased by this capacitor. If the output impedance is designed to be small at the nominal frequency, the output voltage can be raised by varying switching frequency. In this way, a new LLC resonant converter was developed which resonates on the secondary side and use current double rectifier and is connected to this capacitor. Now, for such a circuit, the operation is predicted from the current path of half cycle. The horizontal axis shows the time and this waveform, this red waveform show switch 1 current and switch 1 voltage, this blue, and this waveform show blue is switch 2 voltage, drain source voltage and drain source current. Then and this waveform show voltage of transformer of secondary side and current of transformer of secondary side. And this waveform show current of condenser CK and voltage of the condenser CK. And last, this waveform red show diode 1 current, and this blue show diode 2 current. Mode 1, current flow in such path. The point in this mode is that only one diode 1 turn on. Mode 2, current flow in such path, and the current on the primary side flow in the same direction. Mode 3, current flow in such path on the primary side is parasitic capacitor of the switches is charged and discharged. Mode 4, current flow in such path and current pass through the parasitic diode of these switches. This is the behavior of the current at half cycle. Analysis from the current path shows only one diode is passed in rectification, and the sort switch is possible. It is checked boost mode could be realized using equivalent circuit. Based on the power consumption, the rectifier is replaced by equivalent resistor, and the converter can be converted to such an equivalent circuit using FHA, and then the parameter the express like this. Using this equivalent circuit, investigation will be carried out. Is it possible to design the output impedance to be small as a nominal frequency and still achieve the boost mode? The equivalent circuit shows that the output impedance can be small at the resonance point of this resonator, and then using this equivalent circuit, the dependence of the voltage gain on frequency was calculated. This graph shows the dependence of voltage gain on frequency when the capacitor of CK is varied under these circuit conductions. The horizontal axis expresses the switching frequency, and vertical axis shows output voltage. Looking at this characteristic, even if you design this converter to have very small output impedance at the nominal frequency, you can achieve the boost mode operation. For example, although this is far from the reality for a specific application, the resonance voltage under these conduction has been compared. This navy blue is a conventional LLC resonant converter resonance voltage of capacitor CR, and this blue waveform show resonance voltage of proposed LLC resonant converter of capacitor CR. This waveform show horizontal axis express time and vertical axis express voltage. The capacitor voltage of the resonator is significantly lower than that of conventional LLC resonant converter. There is okay, thank you. Verification is carried out to check the operation under following conditions. This verification was carried out to investigate to these 3 points. First is soft switching is possible, and second is boost mode can be realized. Third is current can only pass through only one diode to dictation. Please look at this result of experiment. The horizontal axis express time and vertical axis express voltage or current. The primary voltage waveform of the transformer, this voltage is shown in blue. The primary current or waveform of the transformer is in red. The waveform shows the current delay relative to the voltage. So the load seen from the primary side of the transformer is inductive. So this circuit can be short switching. Next, please look at this characteristic. The horizontal axis express switching frequency and vertical axis shows output voltage. This blue line shows the resonance points of resonator. This resonator, where the output impedance is very small. Thus, looking at this characteristic, this circuit can achieve the boost mode operations. Now look at this waveform. The horizontal axis express time and vertical axis express current. This red waveform shows diode 1 current, and this blue waveform shows diode 2 current. The verification results show that there is no section where both diodes are not turned on at the same time, as only one diode current passes through during rectification. This circuit can achieve high step-down ratios. Finally, this is the conclusion. Background. In recent years, there has been more demand for DC-DC converter for server power suppliers. So we want to use LLC resistant converter as a converter of server. However, if you achieve the high response, if you achieve the quick response, it have a very high level resonance voltage. So we consider the new LLC resistant converter that using secondary side resonance and current driver rectifier. This capacitor. Conclusion: when we have developed a new LLC resistant converter that suppresses high level resonance voltage without losing the average advantage of the conventional LLC resistant converter. Thank you for your listening.